My name is Danielle Bragg, and I'm a PhD student at the University of Washington. And I'll be presenting some work that I did in conjunction with Shiri Azenkot at Cornell Tech and Adam Kalai at Microsoft Research. So let's start off with the problem. Small text is hard to read for many people. There are hundreds of millions of people worldwide who are visually impaired or have low vision, where low vision is defined as vision conditions that cannot be fully corrected with glasses. There are a lot of older people who have presbyopia as well. As we get older, everyone's eyes begin to lose the ability to focus, and that's why you see a lot of older people wearing glasses. There are a lot of younger people who wear glasses as well. And to make matters worse, we're moving towards a world of personal computing devices, which have limited screen space and often force text size to be small. So suppose that this is your personal computing device. It might be a phone or a smartwatch, and you have blurry vision. Can you see what this says? It's pretty hard, isn't it? So one solution is to zoom in. But if you zoom in, you lose the complete chunk of text that you're trying to read. And so what you end up doing is panning around a lot. It's pretty inconvenient. Another example of the difficulty of small blurry text is if you're texting a message to a friend, for example, and you're not sure maybe if you wrote the word message or massage. Without blurry vision, you can easily double check your text to avoid embarrassment, but with blurry vision, it's not so easy. So here it's basically impossible to distinguish the difference between the second character in each word. But what if we just throw out these letter forms entirely and start from scratch? Can we improve the reading experience? The traditional Latin letter forms, which is what we think of as English, and it's the same letters that are used in other languages like French and Spanish, they're ancient. So can we do better? So for example, suppose we replace the words message and massage with these chunks of text. Here we've replaced each letter with a new letter, and if you have blurry vision, it's still very easy to tell the difference between the two. You can see that one has a small black character and the other one has a taller red one. And here are some other examples of ways that you could replace characters and still maintain distinguishability under blur. And I'd like to point out that there's the same level of blur used on the right-hand side here in all of the different fonts. So you can see that it's much easier when you use things like color. And we call these character redesigns Smartfonts. So Smartfonts replace traditional letter forms with new letter forms to improve the reading experience in some way. And in this work, all of the Smartfonts that I'll be talking about are one-to-one mappings. So each traditional letter Latin form, for example an A, is replaced with a new character, for example, a blue shape. A B could be a triangle, or a C could be a sun. These are just random examples, but they could be anything. And because it's a one-to-one mapping, spelling, grammar, and punctuation can be preserved. So you're not actually learning a new language, you're just learning a new script, a new reading and writing system, similar to cursive or Braille. There are many potential benefits to learning Smartfonts, or to using Smartfonts. You can fit more text comfortably on small screens, potentially. That was the motivation that I started with. You could potentially reduce fatigue. You can design things that are easier in the eyes. You can personalize text appearance, so I can be reading one script while you're reading another. You can increase privacy by using a script that nobody else knows how to read. Nobody can look over your shoulder and see what you're texting if you're using a smartphone, most likely. You can improve aesthetics, and they can just be fun. In our studies and talking to people, there is a population out there who finds reading and writing in their own script a lot of fun. But in this talk, I'll be focusing on fitting more text comfortably on small screens under blurry vision in particular. So to give you a feel for how Smartfonts might be used in the world, here is an example. We uploaded some of our Smartfonts to a Chrome extension that changes all your browser text to that smart font. So this is the Japan Times in a smart font. I think it's the news from yesterday. And if I go to YouTube or anywhere else, it would look similar. Adam, one of my collaborators, also programmed his smartwatch to render text and emails in another smart font. So you can see here, one person can be reading one thing while somebody else is reading another, and there's no conflict there. One question you might ask is, why are we doing this now? The primary reason is that the ways that we interact with text have evolved since our ancient letter forms were created. So in particular, we use computers now, and screens support richer displays that are more easily rendered than with pen and paper. And also we type, so we don't have to constrain ourselves to letters that are easily written by hand. So personal devices also allow individual use without mass adoption. So people have tried to do character reform or language reform in the past, and those efforts have largely failed because you need everyone to adopt it for it to be successful. You have to reprint all the books. It's just not practical. But today, everyone has their own device, and you can set it up however you want. And in addition, smartfonts do not require special software. So you can export smartfonts in standard font file formats like TTF and plug them into your existing infrastructure without any additional changes. All right, so I've already breezed through the problem that we're addressing, which is the readability of small, blurry text. The solution that we're proposing is Smartfonts, which are redesigns of the character displays. And now I'd like to talk a little bit about how we can design smart fonts. So the design space is virtually unlimited, and we want to design these in a principled way. We want them to be both legible and learnable, and that's important to keep in mind as I'm talking. They need to be legible so that they actually help people read, and they need to be learnable so that people can adopt them. And there's an intrinsic trade-off between legibility and learnability. The more Latin-like the characters look, the more like English, the easier they will be to learn most likely, but the amount that they can help legibility will be limited because you're limiting them to traditional letter forms, more or less. All right, so now we'll talk about our designs. So in this work, we designed 5 smart fonts, and you can see them on the screen here. At the top is the Latin alphabet, and below are the 5 that we designed. In this talk, I'll be explaining how we designed Tricolor, which is this last one on the bottom. But if you want to learn more about the others, find me later or check out our paper. All right, so Tricolor uses 2x3 letter forms, and the basis for this goes back to Braille. So people originally made text accessible to blind people by printing embossed letters, and those were traditional letter forms. Then Louis Braille in 1824 was a blind man in France who found that characters made of 2x3 formations of raised dots were much more legible to his fingers. And so he came up with Braille, where each letter is encoded as a 2x3 configuration of raised dots. And what you see with your eyes when you have blurry vision is actually quite similar to what you feel with your fingers. The spatial resolution of both is quite low. So we thought that we would take this 2x3 structure and adopt it for blurry vision. And we filled in the circles, or we expanded them to be squares just to make the most of our ink space. And this is the alphabet that we came up with, or at least these are the shapes that we came up with. And we picked these shapes from all possible 2x3 configurations to resemble the Latin letters that they represent. So you can see the A kind of looks like an A, the B kind of looks like a B, and so on. And the reason for that is to support people learning it. We don't want it to be too hard to learn. Then we realized that we could add color to our smart font to make it even more legible. So we're already using these 2x3s, which we think will improve legibility, and now we're going to add color. And we determined the colors by running a study to figure out which character shapes are easily confused, and then coloring commonly confused shapes differently. We ran a perception study to gather data to back this up. The study consisted of a target and a keyboard. The keyboard was randomly chosen from all the possible 2x3 shapes. The target was randomly chosen from the keyboard. And the participant's task was to transcribe the target using this keyboard. We recruited participants from Amazon Mechanical Turk, and the task started out large and gradually decreased in size, kind of like a Snellen eye chart test that you might have had to do at the doctor. You start out with one large letter, and slowly the letters get smaller as you're identifying them. And the target length ranged between 1 and 9. And again, we decreased the size because we wanted to collect data near the point of failure to figure out what's actually confusable. So we had 548 people participate. From them, we gathered a little over 4,000 evaluations. Each character was shown between 370 and 500 times. And with that data, we computed a confusion matrix. So each row is the displayed character in the target, each column is the character that was selected as a match, and each square represents the fraction of times when the row's character was displayed in the target and the column's character was selected as a match. So the red line along the diagonal is good. It means that characters were often seen as themselves. All right, so we took that data and we looked at the rows and columns representing the 26 characters that we're using in this font, and we partitioned the original 26 characters into 3 groups so that we minimize confusion within the groups. We used a branch and bound algorithm to bound our search space, and this is the coloring that we came up with. So the characters in each group received a different color. This is a 2D visualization of the characters, where similar characters are located near each other. And you can see these 3 characters, for example, are similar in shape, but now they're colored differently. So if you're reading, you're less likely to make mistakes. And here's the final alphabet. So again, we've designed it to be both learnable, meaning that it represents the Latin letter forms, and legible by using these 2x3 shapes with optimized color additions. All right, so now you've gotten a feel for how we can design Smartfonts in a principled way. And next, I'd like to talk about the question, can Smartfonts improve legibility? All right, so do they work? We wanted to run a legibility study to help answer this question, but there were some challenges in the design. Primarily, nobody knows how to read Smartfonts. So how are you going to evaluate a reading and writing system that nobody knows? Secondly, comparison to Latin is unfair because participants will have had a life of experience in reading Latin, most likely. And traditional legibility tests largely don't apply. Most legibility tests ask you to read some text and answer some comprehension questions, or at least identify letters. But again, people don't know how to read these scripts, so that doesn't work. So the design that we came up with is a matching task. It consists of a target, which is a random sequence of 5 characters, which is roughly the average word length in English. Then there's 4 possible answer choices. Each is different from the target in 1 character. And then there's the correct answer, which is exactly the same. And we blurred the answer choices to simulate blurry reading conditions. And this allowed us to use crowdsourcing to rapidly test and iterate on our designs. We used a within subjects study design where each participant was viewing one Smartfont in Latin, which was displayed in Helvetica. Again, we used a decreasing answer size in the test, similar to an eye chart exam. And again, we wanted to determine where people failed. So we asked 3 questions at each size, and we did that so that we could determine with some certainty where they're failing. And we defined the failure point to be the first size where they're making a mistake on 2 out of 3 of the questions. We fixed the blur throughout using a Gaussian blur, and fixing the blur in this scenario means fixing the radius of the blur. All right, so again, we recruited from Amazon Mechanical Turk. We had 154 participants, varied gender and age range, and here's a plot of our results. So the x-axis here represents area squared, which is pixels squared, and we used that because different fonts have different heights and widths, and different combinations of characters also have different widths in particular. Then we computed the percent of participants who successfully answered at least 2 out of 3 questions at each size correctly. And to give you an idea of what area means, this vertical line corresponds to the default Chrome browser size for Facebook. And we found that at that size, with the blur that we were adding, only about 6% of participants were getting 2 out of 3 matching questions correct in Latin, but over 60% were getting at least 2 out of 3 correct with our Smartfont Tricolor, which is the one that I've been highlighting in this talk. So that's encouraging. That's providing evidence at least that these smart fonts can help improve legibility. But what about learnability? Great, they're easier to see, but can people actually learn them? So again, we designed a study to figure out if these are actually learnable. And we designed a website where each person was learning a single smart font. The website provided a tutorial which consisted of the alphabet, the structure of the language, and examples, yes/no questions in the smart font, and flashcards. And our main metric for learning was participants' answer speed for yes/no questions. So a bit more about these yes/no questions. They were crowdsourced from MindPixel, which is a database of yes/no questions, which we supplemented with questions from Amazon Mechanical Turk. We had almost 3,000 with roughly equal yes and no answers. And they were typically fun questions. So this one, for example, reads, do fish wear clothing, yes or no? We deployed on Amazon Mechanical Turk. We had 23 participants, 8 learned Polkabet, 9 learned Logobet, 6 learned Tricolor, which is the smart font I've been highlighting. And they spent 2 to 3 hours per day for about 1 week, which is not a huge time commitment for learning a new script. And here are the results. So again, the y-axis shows the time that it took them to answer these yes/no questions, and we normalized by the average time it took each participant to answer questions in Latin, since each person has a different natural reading rate. The x-axis is the question number, so all our participants answered at least 2,000 yes/no questions. And for Polkabet, participants were about 6.7 times slower after 2,000 practice questions. For Logobet, they were about 5.2 times slower than Latin. And for Tricolor, which I've been highlighting, they were about twice as slow, which isn't too bad after 1 week of practice. So the takeaway is smart fonts could work. I've provided evidence that they can help legibility. We moved from 6% of participants identifying Latin correctly to over 60% at standard browser size, and we've shown evidence that they are likely to be learnable. A lot of participants were at half the Latin speed after 2,000 questions. So some items for future work that I'm just going to mention briefly since I'm running out of time. We'd like to explore privacy implications, since if you're reading a smart font that no one else knows, no one else can read it. We'd like to do a controlled evaluation with low vision participants. We simulated blur, but we'd like to try these out with people who actually have blurry vision. We'd like to do a longitudinal evaluation to see what happens if people actually use these for a long time. There is opportunity for personalizing these smart fonts, since each person's vision is different. Expanding beyond A to Z to include digits, punctuation, other languages, and making them available for download. So thank you, and any questions?
We have time just for one quick question. I see some.
Mike Terry, Google. So really cool stuff. It's an interesting design space. Have you considered things like encoding common bigrams or trigram characters as a symbol, or verb tense as a different color, or a different suffix to a verb root?
Yeah, so that's a great question. I should have listed that as future work. We have talked a bit about that. So, for example, in Braille grade 2, they make use of contractions to save space, and that would be a great space to optimize over. Some participants also suggested mapping different characters to different Latin characters to smartphone characters based on their whether they're vowels or consonants and things like that. So, yeah, those are great ideas for future work.
Second question, why
Hi, great talk. I'm talking about Kalai. I'm wondering if any of your Korean friends will let you know that your characters are really Korean out there?
You said you're Korean? Okay, you know more about Korean than I do, but I mean, yes, we're aware that Korean is a younger character system, or at least there is a younger Korean character system out there, and that's actually something that's encouraging for this work because people have adopted that. So.
Maybe one way to use color is to distinguish a consonant from vowels.
Yeah, no, that's a great idea. Thanks.